Let's understand compass needle placed in a uniform magnetic field. Suppose we want to determine the magnitude of B accurately. This is done by a small compass needle of known magnetic moment M and moment of inertia I. Place the compass in the magnetic field and allow it to oscillate. The torque on the needle is tau equals to M cross B. So, the magnitude of tau is equal to mb sine theta. Here, tau is the restoring torque and theta is the angle between M and B. Therefore, in equilibrium, I into d2 theta by dt2 is equal to minus mb sine theta. Now here, the negative sign with mb sine theta implies that the restoring torque is in opposition to the deflecting torque. For small values of theta in radians, we can approximate sine theta as theta and hence get I into d2 theta by dt2 is almost equal to minus mb theta, or d2 theta by dt2 is equal to minus mb theta divided by I. This represents a simple harmonic motion. The angular frequency omega is equal to root over of mb divided by I, and the time period will become t is equal to 2 pi into root over I by mb. That is, t square is equal to 4 pi square into I by mb. So, b is equal to 4 pi square into I by m into t square. This is the expression for the magnitude of the magnetic field. Expression for magnetic potential energy. An expression for magnetic potential energy can also be obtained on lines similar to electrostatic potential energy. The magnetic potential energy Um is given by integration tau d theta, that is equal to integration mb sine theta, which is equal to minus mb cos theta. Taking the constant of integration to be 0 means fixing the 0 of potential energy at theta equal to 90 degree, that is when the needle is perpendicular to the field. Equation shows that potential energy is minimum, that is equal to minus mb at theta equal to 0 degree, most stable position, and it is maximum, that is plus mb at theta equal to 180 degree, most unstable position. You can see it in the following visual. Example 1. In the shown figure, the magnetic needle has magnetic moment 6.7 into 10 to the power minus 2 ampere meter square and moment of inertia I equals 7.5 into 10 to the power minus 6 kg meter square. It performs 10 complete oscillations in 6.7 seconds. Then what is the magnitude of the magnetic field? Solution: the time period of oscillations is t equals 6.7 divided by 10, that is 0.67 seconds. We know B equals 4 pi square into I divided by m into t square. Putting the values, we get B equals 0.01 Tesla. Example 2. A short bar magnet placed with its axis at 30 degree with an external field of 800 into 10 to the power minus 4 Tesla experiences a torque of 0.016 Newton meter. Then question A. What is the magnetic moment of the magnet? B. What is the work done in moving it from its most stable to the most unstable position? C. The bar magnet is replaced by a solenoid of cross-sectional area 2 into 10 to the power minus 4 meter square and 1000 turns, but of the same magnetic moment. Then determine the current flowing through the solenoid. Solution. As we know, tau equals mb sine theta. Here theta is 30 degree, hence sine theta is half. Thus, 0.016 equals m into 800 into 10 to the power minus 4 into half. So m comes out to be 0.40 ampere meter square. B. As we know, the most stable position is theta is 0 degree and the most unstable position is at theta equal to 180 degree. So work done is given by um for theta equals to 180 degree minus for theta equal to 0 degree, and it comes out to be 0.064 joule. C. As we know, ms is equal to nia. From part A, ms is 0.4. Therefore, I comes out to be equal to 2 ampere. Concepts. A. What happens if a bar magnet is cut into two pieces? Number 1, along the transverse to its length. Number 2, along its length. Answer. In either case, one gets two magnets, each of with a north and a south pole. B. A magnetized needle in a uniform magnetic field experiences a torque but no net force. An iron nail near a bar magnet, however, experiences a force of attraction in addition to a torque. Explain why. Answer. No force if the field is uniform. The iron nail experiences a non-uniform field due to the bar magnet. There is induced magnetic moment in the nail, therefore it experiences both force and torque. The net force is attractive because the induced south pole in the nail is closer to the north pole of magnet than induced north pole.